we're often interested in relating two vector spaces by looking at functions between them. So as an example of why you want to do that, you know that the vector space R cubed consists of height 3 column vectors, so things that look like this. And you know another vector space, so 1 by 3, M1 by 3 of R, the space of 1 by 3 row vectors, where a typical element might look like A, B, C for some 3 real numbers A, B, and C. And it's clear that these are basically the same vector space in some sense, but how could we make that precise? Well, one way would be to look at the map between them given by the transpose. Now, when we think about functions between vector spaces, an arbitrary function won't tell us anything about their relationship as a vector space, because we need to restrict to functions which actually relate the vector space structure. In other words, which respect the addition and scalar multiplication in those vector spaces. These functions are called linear maps, and they're going to be a very important part of the rest of linear algebra. So let's begin with the definition of a linear map. We take two vector spaces V and W over the same field, so they have to be both real vector spaces, or both complex vector spaces, or both vector spaces over the field with two elements, whatever, but they must be over the same field. In that case, a function t from V to W is called a linear map, or a linear transformation, if it respects scalar multiplication and it respects addition. Now, what I mean by that is the following two statements. So first of all, respecting scalar multiplication means that for every scalar, lambda, and for every element, v in big V, t of lambda times v should be the same as lambda times t of v. And secondly, to respect addition means that for every two elements v and w in the vector space V, it must be that t of v plus w is equal to t of v plus t of w. So this is the definition of a linear map, and you actually know many examples of linear maps already, so let's just look very quickly at a couple of examples. So the simplest, or perhaps the most common, is matrix multiplication gives you a linear map. So what I mean by that is, let's take A to be a M by N matrix with entries from a field F. Perhaps F is the complex numbers, perhaps it's the real numbers, but it can be any field. Well then, we can define a map T subscript A from F to the N to F to the M by TA of a height n column vector x is going to be the height m column vector that you get by multiplying x on the left by a. Well then this is a linear map. So the fact that it is linear just follows from standard properties of matrix multiplication. So if we just check the two properties, the first property about scalar multiplication, well, if you look at TA of lambda times x, so lambda is some scalar, some element of the field f, and x is a height n column vector, then by definition that's a times lambda x. But one of the matrix rules we learned right at the start of the previous chapter was that this is the same as lambda times a of x, and of course that is lambda times ta of x. So since this argument is true for any vector x and any scalar lambda, that shows that this map TA obeys property 1. And similarly, property 2 is just a standard property of matrix multiplication. So for any two height n column vectors x and y, if you look for TAX of x plus y, by definition that's a x plus y. But again, one of the properties of matrix multiplication was that it distributes over matrix addition, and in particular a multiplied into x plus y is the same as a x plus a y, which is ta of x plus ta of y. Okay, so these things are true for any x and y in f to the n and any lambda in f, and so TA is a linear map. We'll use this notation TA regularly throughout Math 5, so whenever I talk about TA I mean a linear transformation like this one given by left multiplication by a matrix A. So that's the most important, probably the most important example of a linear map that you'll see. But these things are actually incredibly common, and you'll see them everywhere throughout mathematics. So we'll do a couple more examples in this video, but also, I mean, as a silly example, or not so silly example actually, if you have the derivative of a multivariable function, such as the kind of thing you will learn about in Math 0011 in Term 2 if you're taking that module, then the right way to think of the derivative of a multilinear map is as a the right way to think of a derivative of a function of several variables is via a linear map. So these things really appear in all kinds of different places. Let's see some further examples then. So I want to begin with a map defined on matrices. So let's call this T, which is going to be a map from the M by N matrices over a field F to the space of N by M matrices over F, given by T of A is a transpose. So there are two different T's in here, so it might have been smarter to choose a different name for this. Let's call it F. So here F of A is a transpose. Then the transpose is a linear map. So some standard properties of transpose tell you that if you have any, well, let's write this down properly. So F is linear because for all A and B, M by N matrices, and all lambda in F, we have the following rules for the transpose. So lambda A transpose is the same as lambda times A transpose, and if you have A plus B transpose, that's the same as A transpose plus B transpose. So another way to phrase those identities would be to say that F of lambda A was the same as lambda times F of A, and F of A plus B was the same as F of A plus F of B. So this one says F of lambda A equals lambda F of A, and this one says that F of A plus B is F of A plus F of B. So what we have here is an example of a linear map. Let's try another one. So we'll take the example of differentiation. So this is another example of a linear map which you've already met, and the fact that differentiation is a linear map follows from standard properties of derivatives, which again you already know. So for us, let's take a map D from the space of all polynomials in one variable x to the same vector space, given by d of a polynomial f will be the derivative, so df by dx. So for example, d of x squared plus 2 would be the polynomial 2x. And now this is a linear map. And that's just because of standard properties of differentiation. If you differentiate, so a constant times a function, you get the constant times the derivative of that function. So property 1 of linearity follows because if you have d of a scalar multiple of f, that's d by dx of lambda times f. And because lambda is a constant, it's a real number in this case, then just by ordinary differentiation rules, that's lambda times df by dx, which is of course lambda d of f. So that is the first rule of linearity, the first part of the definition of linearity. And similarly, it's a standard differentiation rule that if you look at the derivative of f plus g, then that's the same as the derivative of f plus the derivative of g, which here is d of f plus d of g. So this is true for any f and g in the vector space we're talking about and any real number lambda. So because of standard differentiation properties, the differentiation map on our vector space of polynomials is a linear map. It's another example of a linear map. Let's try a couple more. So we'll try one more thing which is a linear map, and then we'll do an example of something which isn't a linear map. So let's define a function t from r squared to r by t of the vector x, y is equal to 2x minus y. Now, I'm not going to do this one, but I'm going to leave it to you to check that t is linear. So you should check both property 1 and property 2, and just a little bit of algebra will show you that this thing is an example of a linear map. But let's look now at some examples of things which are not linear maps. So what would it mean for something not to be linear? So it's got to fail one or more of the two linearity conditions. So let's look, for example, at maps which involve squaring. So if we have t being the function from square n by n real matrices to other square, well, let's take 2 by 2 for the sake of being concrete, to 2 by 2 of r, given by t of a is a squared. This thing is not a linear map. In fact, it doesn't obey either of the linearity conditions. So let's look just at an example. If you looked at, for example, t of 2 times a for some non-zero matrix A, then that would be 2a squared, and that's the same as 4a squared. But in general, that's not going to be the same as 2 times t of a, which is 2a squared. So if you've got any matrix where a squared is not 0, then those two things won't be equal. So t of 2a not the same as 2t of a in general. It's another example of something which is not a linear map. Let's take, what should we do? We'll have our function t again from the real numbers to the real numbers. So the real numbers are a perfectly good vector space, a perfectly good real vector space, a one-dimensional vector space. We could take t of x to be equal to, for example, absolute value of x. Then this wouldn't be a linear map. Again, it's not linear. And the reason it's not linear, well, again, it doesn't obey either of the rules in general. So just to take a single example where it might fail, we could do pretty much the same thing as we did in the previous example. So t of, we have to be a bit smart this time, but let's think about what might happen if you had a negative scalar. So t of minus 2 times 1, that's equal to absolute value of minus 2, which is 2, but minus 2 times t of 1 will be minus 2. So these things are not equal, and therefore t is not a linear map. I mean, it also doesn't obey the other linearity condition. I've got room for one more, so let's fit one more example in. So if we took, for example, let's have something that looked a bit more linear. So I'm going to have another function from the real numbers to the real numbers. And this time I'm going to say that t of a real number x is 2x plus 1. Now if you graph this, it's a straight line. So you might think, well, straight line, like it must be linear. But again, it's not linear. It's not linear with our definition. And there's a really simple way to see this. I mean, it just doesn't satisfy that, for example, t of 0 would be, how should we do this actually? Let's do t of 0 plus 0. What's that? That's t of 0, which is 1. But t of 0 plus t of 0 is 1 plus 1, which is 2. And those two things are not equal, so t doesn't satisfy the additivity property. It doesn't respect vector addition. So you have to be a little bit careful with the word linear. When we talk about a linear map or a linear function, or when we say, or a linear transformation, or when we say a function is linear in this module, we mean strictly that definition that we saw on the second slide in this module, in the second slide of this video. So this function, for example, despite having a straight line graph, is not a linear function.